One formula that connects them all. One formula to rule them. One formula to solve them all. And in finance, bind them.
Hi everybody, just trying to channel Tolkien and Lord of the Rings today. But I hope you do get the point. Today we're not just going to talk about math, we're uncovering the mathematical backbone of nearly every discounted cash flow model you've ever seen. Whether it's annuities, perpetuities, dividend discount models, or even full-blown equity valuations, it all ties back to just one elegant formula, the sum of a geometric series. So let's start. A geometric series is just a sum like this. It's S equals A plus AR plus AR squared plus A cubed, so on and so forth. Here, A is the first term, R is the common ratio. But how do you get R? Just divide any term by the previous term to get R. In this example, say we pick AR squared, and let's divide that by the previous term, AR. Then we will get R. And if you do that for any term, you'll find out that it's always R. So this is the sum of a geometric series. Now, let's use a neat trick called the telescoping method to simplify the formula. First, we multiply S by R, then subtract RS from S. We get the following equations, and notice how the in-between terms cancel out, leaving us only with the first term and the last term. In effect, it's like this long telescope, which we simply collapse by folding, and we see only the first term and the last term, the first lens and the last lens. That's the term telescoping method. Now, solving for S, we have the formula for the sum of the geometric progression, where A is the first term, R is the ratio, and N is the number of terms in the summation. Here, for example, what is the sum of the numbers from 2, 4, all the way up to 32? So, using the formula, we get S equals 62, where the ratio is 2, and there are 5 terms, so N equals 5, and the first term is 2. Now, why is this important in finance? Because we're always looking for the present value of future cash flows. So for regular cash flows, this is just a geometric series in disguise. Not for our exercises, we will still focus on annual cash flows with an annual compounding rate. In the future, we will talk about compounding and cash flows more frequent than once a year. Now let's try to expand this and see how it works with ordinary annuities, where all payments are paid at the end of each year. For now, we'll focus on a payment of one every year to keep the notation simpler. Anyway, we can always extend to a cash flow of C by multiplying the results here by C in the future. Now, using the general formula with the first term of 1 plus I raised to the power negative 1, which happens to be the ratio as well, and with n terms, we have the following formula. Now, some annuities are paid at the beginning of each year rather than the end, in which case the series looks like this. This time, the first term is 1, the number of terms and the ratio being the same as the previous case. Note that in the end, the formula is just 1 plus I times the formula of an ordinary annuity. Other books might show more complicated formulas, but we'll just stick with this one so that you don't have to memorize all kinds of formulas. Happily, in Excel, this can all boil down to one simple function, the PV function. The inputs are rate, N per, PMT, FV, and type. And they're all pretty self-explanatory. Just two things to note. One, if you leave the last input blank or put 0, the PV function will provide an ordinary annuity. If you put a 1 in type, it becomes an annuity due. Secondly, the payment you enter will have to be negative if you want a positive PV value and vice versa. This is in keeping with the convention that cash inflows and cash outflows should have different signs. So if you want to have a positive value for the PV function, enter negative cash flows. Please check out the spreadsheet we shared in the video description below to access the Excel files containing the exercises here. Now, here let's first talk about payments of 1 for 5 years and compute using the PV function. We're also sharing a spreadsheet solution to double check the formulas we are using here. And again, check the video description below for that spreadsheet. Note that the annuity due is simply 1 plus I times the ordinary annuity as mentioned before. Extending this to cash flows of 100, we see that all the numbers simply just scale up with the cash flow. Now it's 100 instead of 1, but the computations just get scaled. Now, what if we use FV in the formula like so? Then we're dealing now with plain vanilla bonds. Here it's assumed that FV, the future value, is paid at the end of the period, so alongside the last 100 considered as coupon payments. PV here actually provides the price of a bond. Cool, isn't it? So essentially, you can consider a bond as nothing more but an ordinary annuity plus a lump sum payment at the end of the period. And therefore, this gives us another approach at computing the price of bonds with annual cash flows. What if the annuity goes on forever? Say a payment of 1 at the end of every year. Forever? Well, we know that 1 over 1 plus I is less than 1 if I is positive. And if we keep on raising that number by bigger and bigger exponents, the results move closer and closer to 0 as shown here. So with really big values of n, or as n approaches infinity, we can just think of 1 plus I raised to the power negative n as approaching 0, and for all intents and purposes, we consider it as 0. And this leaves us with a simple equation, 1 over I. So for this kind of forever cash flows, the formula is just 1 divided by the interest rate I. And these kinds of cash flows are called perpetuities. Here at 10%, there is a present value of 10 from 1 over 10%. That's the present value of 1, the end of every year forever. Now, we will extend this discussion of perpetuities and discuss valuation models for the equity markets. For example, we can think of a stock that's a dividend-paying stock, paying out a dividend D forever. Now, theoretically, the price of that stock can be valued as just the present value of a perpetuity of dividends at an amount D. In this case, if the constant dividend is 50 and the interest rate for discounting is 10%, then the price of the stock is equal to 50 all over 10% or 500. Now, what's more interesting to find out is what happens if the dividends were growing at rate G% and we're still talking about perpetuities. Is there a solution? First, let's not talk about perpetuities and let's just consider first a short 5-year term as usual. Now, the dividends grow by G and are discounted at I. That means the cash flows and the discount factor can be lumped together in the ratio, meaning the first term has to be 1 plus G and will be discounted by 1 plus I. Next year, the growth is 1 plus G squared and the discount factor is 1 plus I squared. So it's easy to compute using our general formula for S, which will now look like this. I know it looks complicated, but simplifying it is actually pretty straightforward, although it is tedious. We are left with the formula below. Now, what happens if I is greater than G? Then the ratio 1 plus G all over 1 plus I will be less than 1. So again, raising that number by an ever larger numbers, or as we say, as n approaches infinity, then the term 1 plus G all over 1 plus I will approach 0. And therefore, we'll just consider this for really large numbers of n, this ratio 1 plus G over 1 plus I to be just 0 as before. Therefore, the solution is 1 plus G all over I minus G. So we're simply left with 1 plus G over I minus G. Now, this is the so-called Gordon growth model where D sub 0 is last year's dividend, G is the annual growth rate of dividends, and I is simply the interest rate for discounting. Here, the same problem of a 50 dividend last time, but it's now growing by 5% and we're discounting at 10%. This gives the value of the stock at 1,050 coming from 5,250 all over 10% minus 5% or 5,250 divided by 5%. That's how we get it. And that's the price of the stock using the Gordon growth model for increasing dividends that are growing by a constant amount, G%. That's what we have. In Tolkien's world, the One Ring ruled all others. In finance, well, this is the nearest thing to it, the sum of the geometric series. It's the one ring that binds together all of our valuation models. It governs the time value of money. It shapes the annuity and perpetuity formulas. It powers the dividend discount models and the Gordon discount model, etc. It underlies every discounted cash flow with regular cash flows. So next time you see a complex valuation formula, remember, it all traces back to this simple, beautiful pattern, that one formula to rule them all, the geometric series. If you enjoy this kind of mathematical storytelling, well, hit like and subscribe to continue supporting our channel. See you next time.